These incredible images captured by the James Webb Space Telescope. We're told
in the vast expanse of space, where silence reigns and darkness stretches across distances the human mind can barely comprehend, something extraordinary occurred. The James Webb Space Telescope, humanity's most sophisticated window into the cosmos, captured an event it was never designed to witness, a cosmic collision unfolding in real time. Picture the scene: deep space monitoring stations humming with quiet efficiency, data streams flowing steadily across screens, astronomers reviewing what should have been routine observations of a distant interstellar visitor. Everything was normal, predictable, controlled. Then, without warning, a spike. A violent surge of light erupted across Webb's sensitive instruments, a brilliant flare that shattered the calm monotony of deep space observation. In mission control rooms across the globe, scientists stopped mid-conversation. Fingers flew across keyboards, checking and rechecking the data. Was it an error? A calibration glitch? A cosmic ray strike corrupting the sensors? None of the above. The readings were authentic, verified, undeniable. The cosmic heartbeat had just skipped a beat, and Webb had captured every photon of that irregular pulse. Something massive, something traveling at incomprehensible velocity, had just collided with 3I/Atlas, an interstellar visitor already under intense scientific scrutiny. The impact unleashed a cascade of energy, a burst of superheated gas and pulverized ice spreading across the void like ripples on a cosmic pond. This detection represents far more than another data point in astronomy's vast catalog. Webb is a telescope built for patience and precision, designed to peer backward through time itself, capturing the first light of galaxies born when the universe was young. It observes with methodical calm, recording the steady glow of ancient stars and the whispered secrets of light that has traveled for billions of years. It was never meant to catch lightning in a bottle, to witness sudden violence in the present moment. Yet here it was, a chaotic, explosive event captured frame by frame in multiple wavelengths. This wasn't merely about astronomy. This was about witnessing an event billions of years in the making, a cosmic accident that fundamentally changes our understanding of how objects travel, collide, and transform each other in the space between star systems. For the first time in human history, we've recorded an interstellar impact. We've seen one cosmic traveler strike another in the darkness between worlds. To fully grasp the magnitude of this collision, we must first understand what 3I/Atlas represents in the grand scheme of cosmic exploration. Discovered in early 2025 by astronomers using the Atlas survey system, this object earned the designation 3I, marking it as the third confirmed interstellar object ever detected by humanity. The I stands for interstellar, a classification reserved for the rarest of cosmic visitors. Unlike the countless asteroids and comets born within our solar system, forever bound to orbits around our sun, 3I/Atlas is a traveler from somewhere else entirely. It moves on what astronomers call a hyperbolic trajectory, a path that curves through our cosmic neighborhood but never closes into an ellipse. This mathematical signature tells an unmistakable story. This object came from another star system, journeyed through the interstellar void for millions of years, and will eventually exit our solar system to continue its endless voyage through the galaxy. The scientific description of 3I/Atlas reads like something from science fiction made real. Using Webb's near-infrared spectrograph, one of the most sensitive chemical analysis tools ever deployed in space, scientists examined the light filtering through the comet's coma, the glowing atmosphere of sublimated gas and liberated dust particles surrounding its solid nucleus. What they discovered was nothing short of astonishing. The spectral analysis revealed an extremely unusual chemical signature, a carbon dioxide to water vapor ratio of approximately 8:1. To put this in perspective, comets born in our solar system typically show the opposite pattern, with water ice dominating their composition. But 3I/Atlas is fundamentally different. This bizarre chemistry points toward a birthplace utterly unlike our own planetary system, perhaps a formation region in the outer reaches of another star's protoplanetary disk, where temperatures were so cold that carbon compounds froze solid while water remained relatively scarce, or where the initial cloud of material simply had a different elemental composition than the one that formed our sun and planets. Before the collision transformed everything, 3I/Atlas was already captivating the astronomical community worldwide. Every major observatory, from space-based platforms like Hubble and Webb to ground-based giants on mountaintops in Hawaii, Chile, and the Canary Islands, had scheduled observation time to study this rare visitor. They tracked its every movement, watching as solar radiation warmed its ancient frozen surface and caused its coma to expand to dimensions spanning tens of thousands of kilometers. The comet was performing an intricate ballet of sublimation physics and radiation pressure. As it drew closer to the sun's warmth, volatile ices on its surface absorbed energy and transformed directly from solid to gas, bypassing the liquid phase entirely in the vacuum of space. This sublimation process created stunning visual features: sweeping dust tails that caught and reflected sunlight, gas jets that erupted from cracks and vents in the surface like geysers on a frozen world, and subtle asymmetries in brightness that hinted at an irregularly shaped, tumbling nucleus with varying surface compositions. Astronomers studying these variations noticed signs that all was not stable within 3:1/Atlas. The brightness fluctuations suggested internal stress, structural weakness, perhaps cavities where gas pressure was building beneath the surface crust. But nothing in their careful observations, no model or prediction, foretold the cosmic catastrophe that was about to unfold. The universe, it seems, had been holding one more surprise in reserve. The moment of detection unfolded with all the tension of a thriller. Webb's instruments were conducting what should have been routine spectroscopic observations, carefully measuring the comet's light signature to track subtle changes in its outgassing patterns and chemical composition. The data flowed steadily, predictably, building upon weeks of prior observations. Then everything changed in an instant. A sharp, dramatic spike appeared simultaneously across multiple wavelength bands: infrared, visible, ultraviolet. The sudden brightness increase was unmistakable, impossible to ignore. Scientists immediately initiated verification protocols. Could this be an instrumental artifact? A glitch in the data processing pipeline? A cosmic ray strike that corrupted the detector? Every potential source of error was systematically eliminated. The calibration was perfect. The instruments were functioning nominally. The signal was real. As more data arrived, the picture became clearer and more extraordinary. Webb's spectrograph had captured a kinetic flash, the signature of sudden violent energy release. This was followed almost immediately by dramatic shifts in the distribution and velocity of dust particles surrounding the comet. Doppler shifts appeared in the spectral emission lines, indicating that material was being accelerated to high velocities and simultaneously heated to temperatures far exceeding anything the comet had experienced during its approach to the sun. The instruments were telling an unmistakable story, one that sent waves of excitement and disbelief through the astronomical community. A collision had just occurred in real time, and humanity's most powerful telescope had captured it frame by frame across the electromagnetic spectrum. To visualize what happened, imagine a bullet fired through a snowball at cosmic velocities, except the bullet is traveling at tens of kilometers per second, and the snowball is an ancient ball of ice and rock several kilometers across, frozen to temperatures near absolute zero. The projectile, possibly a microasteroid, a dense fragment of ancient planetary debris, or a heavily compacted aggregate of dust and ice, slammed into 3:Atlas with kinetic energy that would dwarf any explosion ever witnessed on Earth. The impact point instantly vaporized, releasing energy equivalent to thousands of tons of TNT detonating in a fraction of a second. The collision created a fireball of incandescent gas and pulverized ice, a plume of material heated to temperatures exceeding several thousand degrees Celsius erupting from a body otherwise frozen at -200 degrees. This superheated material expanded outward in all directions, spreading like a miniature supernova against the black backdrop of space. Webb's sophisticated instrument suite captured every aspect of this catastrophe with unprecedented detail. The spectrograph recorded dramatically broadened emission lines, a telltale hallmark of shock-heated material expanding at supersonic velocities. The geometry of the comet's dust tail shifted almost immediately, the particles' trajectories altered by the sudden injection of new material moving in different directions. The overall density of the coma spiked dramatically as fresh dust and gas flooded into it, then began rapidly expanding outward as pressure dispersed the material. Every wavelength of observation told the same coherent story. Infrared radiation betrayed the thermal signature of warm dust grains. Visible light scattered from countless fine particles created a brilliant glow. Ultraviolet emissions revealed ionized gases stripped of electrons by the violence of impact. The evidence was overwhelming, unprecedented, and scientifically priceless. Something massive had struck 3:Atlas with devastating force, tearing open its ancient structure and exposing material that hadn't seen starlight since this comet formed in another solar system billions of years ago. The scientific community found itself confronting a profound mystery. What exactly had hit the comet? And what secrets would this violent exposure reveal? Understanding the physics of this collision requires examining it through multiple lenses: energy, mechanics, thermodynamics, and structural engineering on a cosmic scale. The impactor delivered kinetic energy concentrated into a relatively small impact point, creating forces that vastly exceeded the structural strength of the comet's icy matrix. The kinetic energy of even a modest-sized projectile, say 10 meters in diameter, traveling at 50 kilometers per second would be sufficient to vaporize portions of the surface instantaneously and send shockwaves propagating deep into the interior structure. But 3I/Atlas was already in a vulnerable state, weakened from within by forces it had been experiencing during its solar approach. As the comet drew closer to our sun, thermal stress had begun fracturing its surface like ice cracking on a warming lake. Solar heating doesn't penetrate evenly. It creates temperature gradients, with the sun-facing side warming while the shadowed regions remain frozen. This differential heating causes expansion and contraction in different regions simultaneously, generating mechanical stress throughout the structure. Additionally, as surface ices sublimated, gas pressure built up inside internal cavities and pockets, creating zones of weakness throughout the nucleus. The impact, therefore, didn't merely create a crater on the surface, it triggered a cascading structural failure, fracturing the entire body and releasing deeply buried ices and volatile compounds that had been trapped in the interior for eons. The aftermath created a spectacular cosmic display that Webb captured in exquisite detail. A fan-shaped plume of dust spread across space, the individual particles following ballistic trajectories determined by their ejection velocity and the subtle influence of solar radiation pressure. As sunlight struck these particles, the pressure of photons, the physical momentum carried by light itself, began pushing them outward, causing the plume to curve and warp like a cosmic fountain. The fine grains responded more dramatically to this radiation pressure than larger chunks, causing the ejecta to separate and sort itself by size as it expanded. Webb's instruments tracked this evolution in real time, watching as the debris cloud transformed from a compact explosion into an elaborate structure of arcs, filaments, and sweeping curves, a dynamic painting of chaos and beauty rendered in dust and starlight against the canvas of space. For planetary scientists and cometary researchers, this collision represents something extraordinarily valuable, a natural experiment conducted at no cost, revealing information that would otherwise require expensive space missions. Studying the interior of comets typically demands sending spacecraft equipped with drills, spectrometers, and sample return capabilities, missions that cost billions and take decades to plan and execute. Now, through cosmic happenstance, nature had performed the experiment for us, exposing the pristine interior of an interstellar object for detailed remote observation. The material unveiled by the collision was ancient beyond human comprehension, matter that had remained frozen and pristine since 3I/Atlas formed in another solar system, possibly before Earth itself existed. As the impact plume expanded and dispersed, Webb's instruments began detecting volatile gases streaming from the exposed interior. Carbon dioxide in quantities that dwarfed anything released from the surface previously, ammonia that suggested nitrogen-rich formation conditions, methane indicating carbon chemistry, and complex organic molecules. Carbon-based compounds of the type that, under the right conditions, can serve as precursors to biological molecules. The spectral analysis revealed surprises that excited astrochemists worldwide. Webb's spectrometers identified molecular emission lines that didn't perfectly match anything cataloged from solar system comets. Some spectral features suggested the presence of exotic compounds formed under temperature and pressure conditions different from those in our planetary system's formation region. These findings lend strong support to theories proposing that interstellar comets are stratified time capsules, with distinct layers preserving different epochs and conditions from their formation environment. The outer layers, weathered by millions of years of exposure to cosmic rays and occasional heating from distant stars, have different chemistry than the pristine interior. The collision had effectively performed an archaeological excavation through billions of years of cosmic history compressed into a few kilometers of ice and rock. The morphology of the expanding debris plume became a subject of intense study in its own right. As ejected material spread outward, solar radiation sculpted it into elaborate structures. Arcs of dust curved gracefully through space, their shapes determined by the interplay between ejection velocity, particle size, and radiation pressure. Filaments of material stretched between denser clumps, suggesting that some of the ejecta retained structural coherence even after ejection. Fans of fine particles spread wide, catching sunlight and glowing brilliantly. As solar photons scattered through this expanding cloud, the light took on different colors depending on particle size and composition. Bright white from larger grains efficiently reflecting sunlight, bluish tints from smaller particles that scatter shorter wavelengths more effectively, reddish hues from organic-rich material absorbing blue light and reflecting longer wavelengths. Webb's mid-infrared instruments added another dimension to the analysis by tracking the thermal signature of the debris. As dust grains ejected from the impact site radiated away their excess heat, their cooling curves revealed information about particle composition and size. Silicate-rich grains cooled at different rates than carbonaceous material. Larger particles retained heat longer than fine dust. By analyzing these thermal properties across thousands of individual measurements, scientists could construct a three-dimensional map of the expanding debris cloud, understanding not just where material was located, but what it was made of and how large the particles were. What began as a single violent moment had become a rich, multi-dimensional data set that will inform cometary science and impact physics for decades to come. The wealth of data emerging from this event allows scientists to calculate fundamental properties of both the impactor and the comet itself. By measuring the mass and velocity of ejected material, researchers can work backward to estimate the kinetic energy delivered by the impact. Even a relatively small projectile, 10 to 20 meters in diameter, traveling at typical interstellar velocities of 50 kilometers per second or more, could deliver devastating force. These calculations, combined with observations of how the comet's structure responded to the impact, allow researchers to estimate the mechanical strength, density, and internal porosity of the nucleus. Was it a solid monolithic chunk of ice and rock, or a loosely bound rubble pile held together primarily by its own weak gravity? The answer lies in how dramatically the structure fractured and how much material was ejected. The exposed chemical reservoirs provide unprecedented insight into how interstellar bodies form in alien planetary systems. The differences in carbon and water ratios compared to solar system comets suggest vastly different formation conditions, perhaps a protoplanetary disk with different initial composition, or formation at much greater distances from the parent star where temperatures were even colder than in our outer solar system. Some of the organic molecules detected might have formed through radiation chemistry as cosmic rays struck the comet during its millions of years in interstellar space, slowly building complex carbon compounds from simpler precursors. Each spectral line, each chemical signature, adds a piece to the puzzle of this object's origin and history. The collision also forces a reassessment of what exists in interstellar space itself. The impactor had to originate somewhere. One possibility is that it was debris from our own solar system, perhaps an object from the Kuiper Belt or scattered disk that happened to be in 3I/Atlas's path. But another possibility is more intriguing. The impactor might have been traveling through interstellar space alongside the comet, possibly even originating from the same planetary system. If true, this would suggest that interstellar space isn't the pristine void we once imagined, but rather contains debris fields, microasteroid clouds, and the shattered remnants of planetary systems dispersed across the galaxy. This would mean that many interstellar travelers might be bombarded and altered by such collisions during their million-year journeys, making each one that arrives at our doorstep a survivor bearing the scars of cosmic violence. The broader implications extend to understanding all interstellar visitors. The famous object Oumuamua, the first confirmed interstellar visitor detected in 2017, exhibited anomalous acceleration that scientists still debate. Could similar impacts, either before entering our solar system or during its passage, have altered its trajectory or caused outgassing that explained its motion? Every interstellar object we observe might carry invisible battle scars from encounters we'll never witness, their surfaces and internal structures modified by impacts and radiation during eons of travel through the galaxy. In the days and weeks following the impact, 3I/Atlas continued to evolve in ways that surprised observers. The comet's brightness fluctuated wildly and unpredictably, brightening and dimming on timescales ranging from hours to days. New gas jets erupted from the surface at locations far from the impact site, suggesting that the shock wave had propagated through the interior and destabilized other volatile-rich pockets. Regions that had been dormant suddenly began outgassing vigorously, contributing fresh material to the coma and altering its appearance in real time. Perhaps most dramatically, the comet's dust tail multiplied. Before the collision, telescopic images showed a single, well-defined tail streaming away from the nucleus. After the impact, observers documented 3 distinct tails pointing in slightly different directions. Each tail represented material ejected at different times and velocities, creating a visual record of the comet's trauma written in dust and ice across millions of kilometers of space. These multiple tails are visual proof that 3I/Atlas is no longer the same object it was before the collision. Its structure has been fundamentally altered. The impact may have done something even more profound: changed the comet's rotation. If the impactor struck off-center, which is statistically likely, it would have delivered angular momentum, potentially altering the nucleus's spin rate, or even the orientation of its rotation axis. Astronomers began analyzing the comet's light curves with new attention, searching for changes in its rotational period or the emergence of new periodic variations that would indicate a wobble or precession. Preliminary analysis suggested that the rotation period might indeed have changed by several percent, though confirming such a measurement requires weeks or months of continuous observation to accumulate sufficient data. If confirmed, this would represent the first time humanity has witnessed an impact event altering the fundamental rotational dynamics of an interstellar object in real time. The most concerning possibility hanging over all these observations is complete fragmentation. The impact created fractures that might now be propagating through the weakened structure like cracks spreading through glass under stress. Combined with ongoing thermal stress from solar heating and internal gas pressure from sublimating ices, these fractures could cause the nucleus to split into multiple pieces. Cometary fragmentation is rare but well documented. Objects like Comet 73P/Schwarzmann-Wachmann 3 have broken into dozens of separate fragments during close approaches to the Sun. If 3I/Atlas fragments completely, it won't depart our solar system as a single coherent object, but rather as a stream of debris, a glowing trail marking its violent end. Every major observatory continues monitoring the comet closely, waiting to see whether it will hold together or disintegrate into fragments before completing its passage through our cosmic neighborhood. This single event carries implications that ripple across multiple fields of astronomy and planetary science. It fundamentally changes how we conceptualize interstellar objects and their journeys through the galaxy. Before witnessing this collision, astronomers tended to think of interstellar visitors as pristine time capsules, frozen relics that had remained essentially unchanged since their formation in distant planetary systems. Now we understand that these objects can be profoundly altered during their journeys, reshaped by impacts, their surfaces gardened by radiation, their chemistry modified by collisions that expose interior material to the harsh environment of space. The implications for astrobiology are particularly intriguing. The collision exposed organic molecules, complex carbon-based compounds that could potentially serve as building blocks for life. When impacts like this occur, they don't just destroy, they also distribute. Material ejected from 3I/Atlas at high velocity might escape the comet entirely, becoming independent particles traveling on their own trajectories. Some of this material might even be captured by planets or moons in our solar system, delivering organic compounds formed in an alien star system to worlds in ours. Over billions of years and countless such exchanges, impacts could facilitate the transport of prebiotic chemistry between stellar systems, connecting the emergence of life across interstellar distances in ways we're only beginning to appreciate. The collision also reveals that interstellar space is more hazardous than previously assumed. The void between stars isn't truly empty. It contains dust, debris fields, fragments from disrupted comets and asteroids, and the detritus of planetary formation and destruction scattered across light years. These hazards could frequently bombard interstellar travelers, altering their trajectories, eroding their surfaces, or even destroying them completely. This means that every intact interstellar object reaching our solar system is, in a sense, a survivor that has endured a gauntlet of cosmic dangers during its million-year voyage. Future studies of interstellar visitors will need to account for this cosmic erosion, recognizing that what we observe might represent only a fraction of a larger population, with many objects destroyed or fragmented before reaching observable space. For astronomy as a discipline, this detection demonstrates Webb's extraordinary capabilities beyond its primary mission objectives. The telescope was designed to observe the distant universe, ancient galaxies, forming stars, and exoplanet atmospheres. Yet here it has proven capable of capturing dynamic, transient phenomena occurring on timescales of hours and days. This wasn't planned or predicted. The observation happened because Webb was pointed at the right target at the right time. This serendipity suggests that as the telescope continues its mission over the coming years, it will likely witness other unexpected events, stellar eruptions, asteroid collisions, perhaps even phenomena we haven't yet imagined. The universe operates on a spectrum of timescales from billions of years to fractions of a second, and now we have an instrument capable of capturing both extremes. The scientific legacy of this event will extend far into the future. The data collected during and after the collision will be analyzed and reanalyzed for decades as our theoretical understanding advances and new analytical techniques become available. These observations provide a reference data set for understanding impact physics in low-gravity environments, the mechanical properties of cometary nuclei, the chemistry of interstellar materials, and the dynamics of dust and gas in space. Every detail captured by Webb, the ejection velocities, the spectral evolution, the thermal signatures, becomes part of humanity's growing knowledge base about how the universe functions at scales both violent and beautiful. There's something philosophically profound about what we've witnessed. This collision embodies the fundamental duality of cosmic existence, destruction and revelation occurring simultaneously, inseparably. One body was torn apart, its ancient structure shattered, its journey through the cosmos forever altered. Yet in that very destruction, humanity gained knowledge that would otherwise have remained hidden for all time. The universe doesn't reveal its secrets gently or on request. Sometimes understanding emerges from violence, from the catastrophic exposure of what was hidden. The cosmos is both creator and destroyer, and often these roles are impossible to separate. For humanity, this event represents another milestone in our species' long journey of cosmic discovery. We built the James Webb Space Telescope to see the universe's beginning, to capture light from the first galaxies, to study how stars and planets form, to understand cosmic dawn. Yet here it is, fulfilling a role we never anticipated, capturing the universe's active present. It's watching the raw mechanics of existence play out in real time. Ancient travelers colliding in the darkness between stars, ice and rock transformed into light and heat. Secrets billions of years old suddenly exposed to observation. The telescope isn't just observing history. It's witnessing the universe continuing to write itself, an eternal story of transformation played out in fire and ice across the infinite void. This moment reminds us how much remains unknown, how many stories the universe has yet to tell. This collision was unexpected, unplanned, entirely serendipitous. It happened because one object crossed paths with another in the immensity of space, and we happened to be watching with the right instrument at exactly the right moment. What else is occurring out there beyond our current gaze? What other cosmic dramas are unfolding at this very moment? Collisions, explosions, transformations occurring in regions of space we haven't yet observed. How many mysteries await only the right telescope pointed in the right direction at the right time? If this discovery captivates you, imagine what Webb might reveal next. The universe is vast beyond comprehension, filled with phenomena we've never seen and processes we don't yet understand. Every observation opens new questions even as it answers old ones. This is the nature of exploration. Each discovery reveals how much more remains to be discovered. Stay curious. Keep looking upward. Continue asking questions. The cosmos has been telling its story for 13 billion years, and we've only just begun to learn its language. The next great revelation might be one observation away, waiting in the data from tomorrow's telescope pointing, ready to reshape our understanding once again. The universe is still being written, and we have front row seats to watch it unfold.